Good morning.
As you can guess from the title, during my talk I continue on our journey into stellar convection and atmospheres. And what I plan to talk about in the next half an hour is the following. First of all, I would like to give a brief overview over the radiation hydrodynamics code I have been working with in recent years, cobalt. Basically commercial. The code has been mentioned already, so I give a little bit more detail. Then I want to give a brief overview about what kind of atmospheres, stellar atmospheres, have been probed so far with 3D hydrodynamical models. Yeah, and then trends, question mark. I really scratched my head about the ambitious title of this conference, New Trends in Radiation Hydrodynamics. And perhaps it's a bit conventional, but I think two things came to my mind related to the increase of computing power and also the increase of code robustness that I want to talk a little bit, namely driving at higher accuracy became, I think, a theme that becomes more and more important in the modeling, and also the inclusion of more physical processes. There are many. I just want to pick one as an example, but I have been recently involved in the formation of dust clouds in extremely cool stellar atmospheres. Of course, as I said, they are more related, for example, to magnetic fields, non-equilibrium chemistry, chromospheres, rotation, stellar rings, of which we will hear during the workshop conference more. Cobalt stands for conservative code for the computation of compressible convection in a box of L dimensions. L is 2 or 3, so it can do 2-dimensional and 3-dimensional models. As we heard before, it has been mainly developed by Bernd Freitag and Matthias Steffen, with contribution of Sven Wedemeyer-Böhm, who's in the audience, Jorgen Lennart, who's also here, Werner Schoffenberger, who's not here, and myself. It provides solutions of the hydrodynamics or magnetohydrodynamics equations coupled to the equation of radiative transfer. The hydrodynamics or magnetohydrodynamics part is solved with the help of approximately Riemann solvers, which has two nice properties. It gives a rather low intrinsic dissipation of the numerical scheme. And it also provides it is rather shock-proof, meaning that it's well suited for handling shock waves. Wavelength dependence can be treated wavelength dependence can be treated in the radiative transfer with a multi-group approach developed by Ockes. And it uses a tabulated realistic equation of state. In recent times, it has been augmented with equations describing the kinetics and transport of molecules and dust grains, as well as non-equilibrium chemistry, and it is strictly conservative in mass, momentum, and energy. Shamefully, I have to put here in parentheses, we were able to achieve this only in the pure hydro case so far. The MHD case needs still some problems. It can apply open top and bottom boundaries, allowing free inflow of material at the bottom and also transmitting to waves at the top. The code can run in two different setups. We heard about these two terms already, namely these local models, mainly mentioned today, this box and the star setup, and global models comprising the whole star in a so-called star in a box. The so-called star in this box setup. The result of these simulations are basically statistical realizations of the flow in the surface layers of the star from the subphotosphere to the chronospheric layers. Standard models nowadays, typically with a resolution of 100 grid points per dimension, can be run in about 1 month of CPU time on a PC type machine, which is not so bad. So, one of the reasons why one can think about including more processes, or, like we heard this morning, perhaps going bigger, running much bigger simulation as has been possible or has been done before.
Sorry, what do you mean by standard models?
Standard models, I mean, say, standard models with a standard sort of standard resolution, or I should have said commonly used resolution of say 1 to 200 grid points per dimension, a few opacity bins for the radiative transfer, say a handful of opacity bins for the radiative transfer. This is what I'm referring to as standard models, without any extras like magnetic fields, dust formation, non-equilibrium chemistry we solve.
Starting from scratch or with an initial state which is already close?
We do both. We do starting from scaled models if we have something available in the vicinity, but the code robustness is now so high that it's also not a problem to take a one-dimensional model, stretch it out in 3 dimensions, add some fluctuation, let it go, and it will also evolve towards the convecting simulation like we see in this example here. This is a typical granulation pattern here. That example is in the sun that we have seen this morning already a couple of times before, so we won't go into it further. Yes, just to remind you, not only these local box models can be handled with cobalt, but also this star in the box, so basically including the whole convective envelope of something like a red supergiant in the computational box. Here an example of the emerging intensity, and this gives a structure of the entropy isosurface in the interior of the star. Okay, this is a HR diagram, which in the of a spectroscopist, gravity versus effective temperature, that's what the atmosphere I'm interested in. About 3 years ago, I did a little poll asking colleagues from different working groups which kinds of stars they are interested in, what they are working on. Here, color code. I don't want to go into what group is doing what, but all what I want to show is the region in this HR diagram which has been covered by hydrodynamical models so far. And as you can see, that basically the main sequence from A-type stars to cool L-type objects has been perhaps the word covered, one should be a little bit careful, probed by 3D hydrodynamical models. What I mean by probed is that not all models are of similar quality. Some are pretty experimental and are quite, say, sort of proof of doability of models in this region. Moreover, one sees here, this is the location of the red giant branch that people have been also working up the way, up the red giant branch, and basically I would say that main sequence and giant branch have been mostly at least probed by hydrodynamical model atmospheres. Important to note, as we have heard already this morning by Remo, also models have been developed not only for solar metallicity, but also for subsolar metallicity. Something that didn't fit into the graph here, and also white dwarfs that we target for these kind of simulations. Just as an illustration, to me, to some extent, it was also an illustration of the robustness of the codes that we can handle the slight parameter range that we are dealing with. This is granulation in a white dwarf, here in comparison to a red giant. Box size, horizontal box size is here, 7.5 kilometers. Grid box size here is 23 solar radii. So we are dealing here with a scale range of 2 times 10 to the 6. Looks impressive, but there's a catch to it. I added now in the diagram that I've shown before a bit more information about the physical processes that one has to battle with. Yes, and we see again here the main sequence here, the giant branch. This line here for solar metallicity gives the region where the typical thermal relaxation time due to radiation is comparable to the hydrodynamical time scale. as Oleg mentioned already this morning, going in this direction becomes computationally expensive since the radiative timescales become very short, and to ensure stability of explicit hydro schemes at least, one is forced to use very small time steps in this region towards A time stars. The situation is much easier in this direction, where the time step is dominated by the hydrodynamical time scale. Below about 3,800 or so, depending on what you call important, degrees, molecular formation becomes important for this opacity, so that one has to deal with it one way or another in the radiative transfer. Below about, I put it here to 2,600 degrees, the formation of dust becomes important. All these models have been done in this local box setup. At some point, of course, sphericity of the star and also effects to the atmosphere become important, which I mark here on this turquoise line. And very, say, at even higher luminosity, one reaches the Eddington limit where the radiation pressure balances the surface gravity. So, looking at it, say, in general, one sees that mostly people have been concentrating on this part, and only quite recently people have been starting to investigate these very cool or more regimes, the more upper regions of the HR diagram.
But this does not include research on disks, which you could also include in such a diagram.
Okay. My topic was stellar atmosphere, so perhaps you're right, and I'm simply not aware of what is going on in the disk community, and I hope that I will learn in the conference a bit about it. This is a diagram, also for me an old diagram, showing how this opacity binning, which has been mentioned, is working. Since people have been talking about it before, I'm not going to explain it. I just, here again, I just want to point out that the basic idea was provided by Orke also in a seminal paper in 1982, and I think it's clear that it has been the workhorse helping us to do the non-gray radiative transfer and this kind of simulations ever since. Big credit to you, Orke. The oxygen story. Okay, I should now say I now picked the two things that I wanted to go a little bit more into more detail is high accuracy and dust formation. This is an example where one would like to have reliable, accurate models. Namely, this is an example, or related to the abundance of oxygen in the sun. What I show here is an important line, strategically important line, for the abundance determination of oxygen in the sun, namely a blend of the forbidden oxygen line at 6,300 angstroms with the nickel line, which is one of the prime abundance indicators of oxygen. High resolution observational material, a spectral resolution of 300,000 and a singleton noise of about 2,000. And what's shown here are the comparison of the 3D synthetic spectrum, the dots, the round dots, in comparison to the observed spectrum here as a solid line. Two observed spectra are given of two observers, and despite one might think the sun is close, bright, the observational material must be perfect, looking at them closely, one sees also differences in the observational material. Looking at these lines has, of course, two purposes. On the one hand side, one can see it as model testing, sees how well models can reproduce the observed features, but, of course, if it comes to abundances, stellar abundances, the abundance is also modeling result, outcome of the model. And in order to be confident, one would like to see perfect fits, or as good as possible fits to the observation material. And you can see this is the best that we, with our Cobalt code, could come up with up to now for the disk-integrated flux spectrum. You see that the correspondence is not exactly as good as one would like. How much time do you have?
Oh, yeah. Another 10 minutes.
10 minutes, okay.
Ah.
A little side point concerning accuracy. If one is driving at high accuracy, one is also confronted all of a sudden with side aspects that one might not have thought about before. I recently ran into the fact that the sun is not a solid body rotator, but a differentially rotating star. And I hadn't expected to see these things on that level, that this is actually providing differences on this scale, but what is shown here is a synthetic line calculated and rotationally broadened, once assuming the sun is a solid body rotator, which is a solid line, and is differentially rotating, which are these green diamonds. And the differences between both line profiles are here shown in the 20 times expanded scale. And one lesson that I learned from this is that surprisingly, that even small details, or that one considers small details as small details, become important when driving at high accuracy. Okay, side remark finished. Now, one thing, also a question that came up this morning, is the question related to the accuracy of the binning scheme. How accurately can one reproduce the thermal structure of a hydrodynamical model atmosphere? I have to apologize for this very busy and I think poor quality plot, but I try to talk you through what is shown here. This is a temperature plot versus optical depth. There are basically three important lines that I would like you to focus on. Here are two hydrodynamical models, one with a black solid line and red solid line, which are calculated with the refined radiative transfer based on 12 bins, and one with 5 bins. And you see, I was surprised to see it, that it makes a temperature difference of about 50 degrees still, this refinement in radiative transfer and the absolute temperature of the mean three-dimensional structure. I also plotted for comparison semi-empirical solar model atmosphere, the Holdiger-Müller model, here by this green line, which is known to reproduce many of the spectral features of the sun very well. For example, the center-to-lid variation in the continuum is very well represented in the Holdiger-Müller model. And from that perspective, even if it's a 1D model, so it's not necessarily the case that the 3D model should fit it exactly, I consider it still as a benchmark that one should approach with a mean 3D structure in order to get a realistic thermal structure of this solar atmosphere. There's still some room between even the refined model and this semi-empirical model. I should also point out that I think this is the best match of a theoretical model I've ever seen with a Holdiger-Müller model. Something about scattering. I would just repeat what Remu said today about scattering in metal-poor giant models. So I skip this. And want to come to my last point, namely the formation of clouds in cool stellar atmospheres. Below a certain temperature, one has to face the formation of the transport of liquid and solid condensates, which shape the thermal and photometric properties of brown dwarfs and extrasolar planets. This is a non-equilibrium process. The condensation and evaporation processes need to be described by kinetic equations, coupled to the transport by the flow by advection, producing also some mixing of the materials. A competing effect is gravitational sedimentation. The small droplets that form in the cool outer layers have, like raindrops on the Earth, tendency to fall back down into the star and try to remove condensative material from the optically thin photosphere. The main feedback of the condensing material happens by blocking of radiation. Dust grains are very opaque, and in the moment they are forming, they have a large absorption cross-section. As I said, block a significant part of the outgoing radiation. This is an ongoing project together with Bernd Freitag and Salar, as well as with contribution by Susanne Hüfner from Uppsala. All what I want to show is the result of a 2D test model. That's how far we got so far, showing the evolution of a dust cloud layer on the top of a convecting, of the convective zone of a brown dwarf. So this is a vertical cut. This layer is about optical depth humidity. Here, convection is going on, similar to what we saw in the sun. Material is rising, reaching a rather sharp boundary layer where the temperature drops to a level that allows the formation of dust. And color-coded, the reddish and bluish color gives the density of dust, and all of a sudden you have strong dust formation. I would like to emphasize that this is a logarithmic scale, meaning the color scale is pretty compressed. Otherwise, you wouldn't see any dust here in this downflowing region. Dust is also dissolved very quickly as soon as dust particles are ejected back into the star. Interestingly, you see how the cloud pattern evolves here, and if one looks closely, one also can see that the clouds are triggering a second convective zone, producing these small scale eddies up here in comparison to the larger scale structures down here. Okay, so I come already to my final remarks, where no conclusions I want to make here, but as I said, some say personal remarks of a Marie Curie fellow working with Orke in Copenhagen for 2 years, about a decade ago now. Just some vivid recollections of these times that I wanted to bring forward here. I'm happy that Orke could make it, is here today, and it was an interesting time. An implicit rule that I learned from Orke at that time was the following. Orke's implicit rule number 1. Don't ask me unless you have read the manual or the source code. This depended a little bit on the context that was discussed. Rule 2 was, if you have read the manual, respectively source code, and you still have questions and email, please consider the fact that our office-to-office distance at that point was about 50 meters. Okay, empirically, I found that on Friday afternoons, rules 1 and 2 don't apply. So it was a good chance to grab Orke for a discussion. However, any discussion was in danger to end abruptly, since he usually forgot for some time some interaction of family matters with the Copenhagen bus timetable. Quite often he shut up, said, "Oh, my son has an important soccer match. My bus," and he rushed out. Somehow untypical today, I was usually some further recollections of working with Orke was that I see Orke always sitting in when it comes to conferences, but at the back, happily programming on his laptop. So today is sort of an untypical situation. Mm-hmm. But perhaps happily programming something he shares also with other scientists, as we see here. I would like to take this opportunity to have my cordial congratulations for your 60th birthday, and also thank Axel for the possibility of speaking here today. Thanks for your attention.
Thanks very much, Hans, for your personal recollections. Immediate question by Christiane, please.
I'd like to know how you're treating the organization setting and what the chemical composition.
As I said, it is just a test model, and the chemical composition was envisioned as being a pure carbon-like dust, but carbon, say I can't just put a label on it, it is not a more complicated chemical compound, it's just the monomers that form, just monomers of some kind forming these dust particles. So a very simplified model, and for example condensation temperatures are put in more or less ad hoc to get a reasonable amount of condensation in this model. As I said, it's just testing the concept, not targeting at really coming up with a realistic model of anything. gravitational settling, it is done in equilibrium speed, meaning the equilibrium speed of a particle is calculated according to its density and size, and is then just added to the flow speed as an extra attractive velocity.
So you're stating that the Lorentz component is also differentiation between dust velocity and the dust.
Yes, it is position coupling except for this extra sedimentation velocity of the particles, which is added on top of the microscopic flow.
Can you just repeat briefly the basics of the question, because some people didn't hear this quite well.
Okay. The question was how the dust sedimentation is treated in comparison to the hydrodynamic flow, I think. And well, the dust is considered as being tightly coupled to the gas, so to moving first order with the gas velocity, plus an extra velocity related to the gravitational sedimentation, which is calculated from the gas particle properties. And this is done by an operator splitting technique, first doing the advective step of the gas together with the gas particles, and then afterwards another step doing the sedimentation of the gas particles. Also the advective step.
Ed?
What do you do about nucleation of the dust?
Good question. I should say I'm not an expert in these issues, but as soon as we assume that as soon as a certain threshold temperature is reached, or one is going below this threshold, efficient dust growth is assumed, meaning that we also assume a certain supersaturation level, so that nucleation is not the first step of nucleation is not preventing the dust formation. So we assume that this nucleation step is already taken below a certain threshold.
How do you put it in there? What do you...
Well, this threshold temperature is, say, at the moment, basically a free parameter. As I said, this is just a test model where we just wanted to see efficient dust formation, and also wanted to see the feedback of the dust formation on the radiative transfer. Because technically, these things were working. This is certainly a further step that needs to be taken.
It was really nice to see all these, this broad, vast range of parameters that, of course, where radiation transfer is important. And I think it's of interest for this conference as well, of course, to realize that radiation transport, which has a long history in stellar physics, has a lot of similarities, although also some important differences in other fields, as we will see in the following days. As part of the discussion in the before lunch, I think the differences in the language, perhaps, between disk physics and stellar physics should be highlighted. But if any other questions emerge, please make notes to bring them up during the discussion. So thanks, Hans, again. And now we have a talk by Young-Chong Cho from Korea. He will be talking about polarized emission from T-Tauri stars to T-Tauri disks in radiated equilibrium. Please.
Okay, thank you for giving me a chance to talk. And I'll talk about polarized emission from T-Tauri stars. And this is our motivation. This is an observation. This is sub-millimeter observation for T-Tauri disks. And as you can see, there should be some disk here and another disk here. And this is the direction of polarization. Means the intensity is strongest in this direction. And the degree of polarization is around a few percent, around 3%. And the direction of polarization seems to be perpendicular to the disk surface and disk plane. So they reported that the level of polarization is around 3%, and they conjectured that this is from aligned dust grains. in the disk, then is it really reasonable? So, and first of all, what are T4I stars? This is the classification scheme for protostellar systems, and this is class 0, and this is the protostar is deeply embedded, and this is called the main accretion phase. And the class 1 is a late accretion phase. Class 2 is it has no accretion disk. The disk is accreting, but it's not main accreting disk phase. And we have protostar and a relatively quiet disk here, and it's optically thick. And this is the debris disk. And the T4I stars are actually these at those phase. So one of the disk models that can describe this kind of disk is that the disk is passive. Passive means that it passively irradiates the radiation from the central star. So in other words, the accretion luminosity is not so important here. What is important is just the re-radiation process. And the disk is flared. Flared means that this is the usual disk scale height, H is scale height, and this is from hydrodynamic, hydrostatic equilibrium condition, and this sound speed and radius. When the sound speed or temperature falls off more slowly than 1 over r, then we can say H is not constant, R over H is not, this is not constant, and this is increasing as R increases. So this is a flare of disk. Okay, so we adopt disk model by this person and this person, these groups. First of all, we have flared disk like this and protostar, and they consider the 2 layers, surface layer and interior. And the radiation from the central protostar hits the surface, and half of the radiation escapes, and half of the radiation enters the interior and hits the interior. So, radiative equilibrium at the surface and also in the interior can determine the temperature of the surface and interior. And so this is the basic idea of radiative equilibrium disk, passive radiative equilibrium disk. Also, there should be hydrostatic equilibrium along this direction. So this is a temperature distribution as a function of radius, distance from the star, and this is the interior, and this is disk surface temperature. And this is their spectral energy distribution, so-called SED. And as you can see here, this is stellar radiation, and surface radiation dominates at short wavelength. Near IR and part of mid IR, and interior dominates at the far IR. And their SED fits observation quite well. And here we use a more sophisticated model of Cheng et al. 2001. There, the only difference is that here they use the fixed grain size. Grain size is only like 0.1 micrometer. But here the idea is the same. Right? There's a protostar and there's a surface layer and there's the interior, and the disk is flared. But the grain size distribution is it follows a sort of a so-called MRS distribution. So a kind of a power law distribution from this size to this size. So the maximum grain size is 1 millimeter. That's natural for accretion disk, T4I disk. And they also consider 2 kinds of grain models. Actually, a little bit more, but basically there are 2. One is just a silicate model. The other is isosilicate. Core is a silicate, but mantle is water ice. So they have a little bit different opacities. And this is opacity. And this is their temperature distribution, and also they calculated SED and other things, and we adopted this model. Okay, let's go back to the motivation. So there are observations and the polarization is perpendicular to the disk, then can you explain this using the disk model? And our answer is yes. When we use T2 disk model by Cheng et al., and if we consider grain alignment by radiation, then we can explain it. So let me briefly talk about grain alignment mechanism. First of all, observation says that grains are aligned. Suppose this is magnetic field lines. These are magnetic field lines. Then grains, if grains are elongate, then this long axis is perpendicular to the magnetic field lines. That's a grain alignment. That's an observation fact. And also, aligned grains can emit polarized emission. For example, if this is electric field, and this strength of the radiation is weaker than the strength of this radiation, because basically this is longer. And here, wavelength is much longer than grain size. And this is infrared because the temperature of grain is just a few hundred degrees. And of course, if there's a mean magnetic field here, then direction of polarization is like this, perpendicular to the magnetic field. Okay, so it was known that radiation can align those grains. Suppose that the grain shape is like this kind of pinwheel shape. Then if radiation is coming from the top, then this one will rotate. Or suppose that the optical properties are different. Then suppose that this one absorbs light, and this one reflects 100% of the light. Then this one will, if we illuminate, then this one will rotate. So radiation can rotate just grains. Then grain and Weingarten showed that if grains rotate thermally, faster than the thermal speed, then they showed that through numerical simulations, they showed that grains are aligned. Aligned means if we have magnetic lines, it's perpendicular. So we calculated grain alignment efficiency for T2 disk, and we used the T2 disk model from Cheng et al. And we used the DD scaffold by grains group, and we used this kind of grain shape, and we did direct numerical simulation. And this is an example of grain alignment. Since I don't have much time, I'll show just an example. And we calculated here grain alignment efficiency, or the rotation speed of the grain as a function of the radius and distance from the star. And here, omega t is the thermal rotation speed, and omega red is the actual rotation speed if there's a radiation. And grain and Weingarten showed that if this is larger than much larger than 1, grains are aligned. So here, maybe this is the line. And we use more like pessimistic criterion, not just the 1, but it's around like 4 or 5. Then here, the thermal rotation speed by radiation is slower than thermal rotation speed, but here it's faster. So we can say, on the surface of the disk, grains here, far from the star, grains in this region are aligned, but grains in this region are not aligned. So schematically, we can say that if this is a disk and this is a top view, then we can say that, and here we assume that magnetic field is toroidal. Then we can say grains are aligned here, and we can say grains are not aligned. Grains are not aligned near the center. So then we can calculate polarization, because we know optical depth at every point in the disk. We know optical depth, so we can calculate emission. And so, for example, for any given line of sight, we know optical depth with respect to this axis and this axis. Then, from 2 calculations, we can calculate the degree of polarization. Actually, we need 2 more. We need to calculate intensities for 4 directions for any given dynamo site. But anyway, in principle, we can calculate degree of polarization and direction of polarization. And here, this is the wavelength, and this is the inclination angle. And as you can see, we can calculate degree of polarization. And this is the SAB, and this is the degree of polarization. And as you, this is theta equals 90 degrees, which means that this is axial disk, and this is a phase-on disk. And degree of polarization varies as a function of theta, but it varies from NH of 50%. That's consistent with observation. Also, we can calculate the radial distribution. Like here, if it's a sub-millimeter, then this one is a polarized emission, and it's dominated by far side of the disk, outer part of the disk. Correct? So basically, this is the conclusion. So radiation can align the grains, and aligned dust grains can produce polarized emissions. And the result is consistent with observation. Thank you.
Mm-hmm. Thank you. Thank you. Harald.
So your dust grains are distributed how, depending on the size of the dust?
That's MRN distribution, and the power law is
No, I mean spatially.
Spatially, that is a problem, but we assume that gas to dust ratio is fixed.
Everywhere.
No sedimentation.
So there's no settling.
Right. Yeah, that's a very complicated issue, so maybe later we can add it, but at this moment it's too hard.
So how important are the big dust grains for your...
That's very important. That's very important because...
but those are the ones that you expect to settle.
Settle one.
Don't to settle in the mid-plane. I mean, you don't expect very big grains in the surface layer.
Right. Then the result may vary, but anyway, the qualitative conclusion will not change, but quantitatively it will change, like a factor of 2, 3%. But at this moment we don't know.
That will probably also apply to radio wave lengths, but maybe only in galaxies, right?
Yeah, right. But here we just focused on sub-millimeter because for radio wavelengths, free emission or synchrotron emission is more important.
Yeah. Any other questions?
Can you allow a large scale colloidal energy?
Colloidal. That's important, but currently nobody knows actually the distribution of magnetic lines. So just here we assume there is a colloidal, and then a colloidal, but if it doesn't agree with the observations, then we should reject it. I mean, anyway, it seems that our model is consistent with the observations, means that magnetic field lines may be colloidal.
But they could also be colloidal.
That's right. That's right.
Did everybody hear the question? The question was whether you could infer colloidal field. Right. So thanks very much for your talk. Now we have a talk by Vincent Icke on something which, as Spiegel thought, could perhaps be a somewhat religious talk.
I know him a long time, you know.
So it's a talk about unstructured grids, in praise of unstructured grids.
This is nothing, all right.
Which will, of course, cover easily all kinds of different disciplines in astrophysics, where we want to go beyond Cartesian grids. So, Vincent is from Leiden, and has been in his...
Well, thanks for the invitation. It's very nice to come to Stockholm again, in particular for this audience. What I should like to talk about, my dear Ed, is about as religious as I get. Because after all, in the meeting is about trends, and so I decided, in reference to the organization, to talk about things that are currently going on, rather than about things that we have sort of achieved. And since I'm talking about that, it should perhaps be appropriate that I, beginning list the people who sort of working with young Peter Paardenkoper, is a young man sitting over there. The other three are sort of left behind in Leiden to moan the weather over there. Those of you who have worked in computational physics know that regular grids are effectively a mental mapping of a mathematical limiting process, and it's the easiest one that people can think of, right? Rather than having lim, etc., etc., etc. Now, those of you who are in observation astronomy may know the most important observational theorem in case of limits for astronomy, that is to say, 1 approaches 2 for large values of 1. With us, that's slightly different. We just have an easy mapping of this sort of thing. Now, the problem with that, of course, is that it's regular, it is anisotropic, and it is non-adaptive. The fact that it's regular, I will get to come back to at the end of my talk, because as I think most of you know, for every regularity, for every symmetry group in nature, there is a conservation law. And therefore, if you impose a regularity on your solution system, you create spurious conservation laws. Now, in hydrodynamics, which is mostly the topic over here, that's not perhaps so bad, but I guess we'll talk about other applications at the end, and you'll see it can be devastating. The anisotropy is awfully nasty, as everyone realizes who has ever tried to do something spherical or cylindrical on a Cartesian grid. And of course, it's non-adaptive. You just simply fix a grid and you leave it where it is. Now, that non-adaptive bit in the most modern hydro codes has been replaced by an adaptive mesh refinement technique. There again, I should perhaps mention that the main theme of my talk, sort of similar to what you see themed over here, and that is, rather than go by convenience, you go by mathematical properties. Right? Now, this type of AMR structure, of course, was so successful because it was modeled after a mathematical tree structure, all right, which makes life very easy. Even so, a grid like this is still regular to a certain extent, and it is certainly anisotropic. Now, what I should like to advocate is the application of what is known as Voronoi-Delaunay grids. A Voronoi tessellation effectively is made in the following fashion. You have a point process, points distributed over here. In this particular case, it's a Poisson process, that's going to be random. And you have a distance recipe. And that distance recipe tells you how far one point is from the other. Now, a Voronoi tile is effectively the locus of all points that is closer, according to that distance recipe, to a nucleus than to any other point. Right? And this is a unique tessellation which has rather nice mathematical properties. It's optimal in very many, many ways. And it is this particular grid that I should like to emphasize in this talk. Now, to go through a few examples, making Voronoi grids is currently, at least in the applied mathematics literature, a completely cut and dried subject. Right? There are very, very good mathematics packages, such as the QHull package, which are in the public domain, which allow you to compute things like this in less than half of no time. Again, you know, when you do things like this, periodicity hardly matters. Only those of you who sort of have very good color and pattern recognition will realize that this actually is periodic, and that the single cell here is about this size. And still, computationally speaking, it looks more or less random, which for practical purposes it is. And the local anisotropy of this is actually going to be one of the main items in my discussion. Making these things finer and finer and finer, again, according to the current techniques, is relatively straightforward. Now, how are we going to apply grids like this? The first application that I should like to show, in fact, is the main thing of this talk, is the so-called dual of this Voronoi tessellation. Every Voronoi tile has a dual, which consists of picking any nucleus and connecting the neighboring nuclei for which there is a neighboring Voronoi cell. This is known as the Delaunay triangulation. It is unique, and again, it has certain very nice mathematical properties. Now, at the outset, I should like to emphasize to you that this to the human eye already looks kind of irregular, right? But for a given number of seed points, this is as regular as you could possibly get, right? If you were to impose a distance, a minimum distance on these various seed points, you're going back to a regular cell structure. In fact, in 2D, it is not hard to show that the regular cell structure corresponding to this is a hexagonal tessellation. In 3D, of course, there is no such thing as a platonic solid that tessellates the plane with the average number of lines that you have here, so there it is intrinsically isotropic. The method that we have used, or designed rather, to use this particular kind of grid was called Simplex by its programmer and inventor Jan Ritzenfeld, and it amounts to transport on a Voronoi Delaunay grid. Now, let me explain in a few steps what this transfer technique really means, and then perhaps discuss a few extensions thereof. The main culprit is Jan Ritzenfeld, who graduated in my theory group a few months ago. To my great chagrin, there is no structural support for theoretical astrophysics in the Netherlands, which is like playing football without a goalkeeper. And so, no, seriously, you may win a match or two, okay, but then you get cream. So, unfortunately, Ritzenfeld decided to take a job in industry. He's now making a small fortune at one of the bigger Dutch banks doing risk analysis. In any case, Jelle called this simplex because the basic item in a triangulation is the mathematical simplex, which of course in 3D is a tetrahedron. Now, the first thing we do, first step, is you represent your transport medium by a point distribution. Those points then serve as nodes in a Delaunay triangulation, and finally you identify a Markov process to go from point to point. Now let me go through these three steps one by one to show you how this works. First, you represent your transport medium by a point distribution. Now that representation, that medium, for instance, could be, as in our case, gas and dust, as in radiation hydrodynamics, but the medium could be something different. If you want to study how data packages get shuttled around on an electronic grid, for instance, like the World Wide Web, your medium would be wires and radio beams and all that good stuff. The medium also might be the vacuum. In the end of my talk, I will show you one possible application of this to lattice quantum chromodynamics. Now, the transport medium is represented by a point distribution. What do I mean by representation? And that's where an interesting trick lies. For instance, one thing you could do is you can refine your point distribution to an almost infinite number of points on your representation volume, and your infinite limit then would correspond to, for instance, the gas density. That, however, does not turn out to be the cleverest thing to do, because you have basically two freedoms to choose. One is you can pick your point distribution. The second thing is you can pick your distance recipe. Now, the more general thing then would be to take the point density of that first process as a function of, for instance, the gas density. And then you can take this function to optimize the transport. I will show you one particular case in just an instant. This simplex method then works, as I already indicated. You start to go from one point to another and you redistribute whatever it is you're redistributing. It could be money, it could be data bits, it could be radiation, it could be anything else, people for all I care. Then this Markov process effectively defines your numerical transport code. That then amounts to the fact that from a given point you get a Markov random walk on this particular grid. Now, we will, in this example, represent our mass density by having a point density process. That's the dth power of the gas density, and d is the number of dimensions you have. It is not too hard to show that if you make this choice, then the expectation value of the edge length of the Delaunay grid is the same throughout the grid, namely it is equal to the mean free path of your photons. That is to say, if you take this distribution, then the grid may to our human eye look extremely irregular. For a photon, however, that grid is as regular as it could possibly get. The scattering distance from point to point is equal everywhere. So the mean Delaunay length in that case is equal to the mean free path. Also, of course, this means that if you write a code like this, it is trivially parallelizable, because every given node in the Delaunay grid is exactly equivalent to every other one. Now, there's one drawback to this, and that is if you do that, the number of points that you have in your representation is fixed, and it is not a step in the limiting process. And it is this that we've had some trouble persuading people of. People typically think of refinement, again, harking back to my first sentences, to this limiting process. You increase the number of points, at least mentally, to as large as your computer can hold, because that is your computational approximation of the mathematical limiting process. Because we make a choice to regularize this grid by making this length equal to the mean free path. We do not have this freedom. We just have a fixed number of points, and therefore our representation is just one instance of a large number of similar ones that we could have taken. So we have an ensemble distribution. In other words, if you want to know the accuracy of the method, what you really need to do is run a few cases where every single time you do the transport, you just simply say that this is one instance of this ensemble of possible point distributions. We tested this in many, many ways. This is a fractal distribution of points. It's a Levy flight with a density ratio of approximately 1 in 10,000. And I'm going to zoom in on the results now, and then these 5 steps. Well, my red color sort of, well, you can still see a little bit over here, I'm sorry. So we've gone in this particular case through 10,000, to a factor of 10,000 in density. Jelle applied this to reionization in the early universe. This shows a result of one of his computations shown in a sort of nice way, where the red stuff here is the neutral hydrogen and the blue stuff is the ionized hydrogen. And as the universe evolves, this particular bit of universe at least, and we can get to look further and further into this particular ball. I have another simulation here where you start with this particular density distribution, which is one of the Munich group, and then you just put gas in it and you do your reionization. And this is kind of a box of the stuff that you get. If you increase the the redshift at which you're looking, you will see, of course, that this stuff gets ionized more and more, right up to the point that it percolates. And Ilya is going to talk later during this meeting about other similar simulations. This was one of 6 of these comparison project that Ilya was the head of. All right. Now, quantitatively, this works reasonably well. Computationally, it works tremendously well. It turns out that had we wanted to do a simulation like this with a regular type of radiative transfer code that you could get just around the corner, we would have taken about 2 weeks on the Netherlands' largest supercomputer we have available. This thing was actually run on a laptop computer in a few hours. Right? It is that fast. Because this grid, from the point of view of the photon, is isotropic and uniform, the method does not scale with the number of primary radiation sources, and therefore converges dramatically quickly. All right, well, we've seen that one. Finally, since we are talking about trends, I will take the liberty to spend my last few minutes on possible other applications of this particular unstructured grid technique. Now, we stick with the Voronoi-Delaunay triangulation because of its nice mathematical properties, and I'm not here trying to advocate this particular form as the only way of doing this. I'm just trying to say that using unstructured grids is mathematically nice. One of the things that we could possibly do, and that we are in fact going to do, is to study situations where the photons are actually carried mostly with the flow. In that case, you do not take your point distribution in such a way that the medium is represented by an equal mean free path between points. You will recall that you do this by taking a point density sprinkling, a point process. the density of which is the dth power, the dth dimension, of the gas density, so the density of the third power in the case of 3D simulations. If photons, however, are caught in the medium, this is not the optimal representation. The optimal choice for this redistribution function is such that you take the d over 2 power. And the reason for this, I think you understand. On a random walk, you get this square root dependence of the number of steps in the random walk. So this distribution, rather than having rho to the power d, does not make the distance between the points equal to the mean free path of the photons, but it makes the mean diffusion time equal between points. So the mean Delaunay length, in this case, is proportional to the photon diffusion time. So from the point of view of a photon in the medium where the photon is carried with the fluid, this is the optimal approximation. One thing that we will be working on, and that is what Kyle Kraut, the second person I listed on my first list, is going to be involved with, is multicolor radiative transfer. There's a lot of that already been said here about this ways of binning opacities. And what you would need to do, of course, is to have a different grid for every single one of those bins, and then you get an extra degree of freedom in that a photon that gets scattered into another bin gets to move to a different plane. Computationally, this is relatively trivial. However, the problem is that if you want to do light transfer, which in this case would be very nice, of course, you have an enormous problem, because the biggest problem is not making your tessellation quick. The biggest problem is not parallelizing your microprocessors. That is all totally straightforward. The problem is that it is the Doppler effect, because you have velocities, okay, the Doppler effect that shifts things in a rather nasty way. So doing Doppler motions in this particular approximation is a problem that we have not yet solved, but that we intend to attack. More exotic other applications are possible. In fact, this simplex method, so the unstructured grid method, is applicable to everything in computational physics that uses grids. All right. Lance-Boltzmann method is something that is well known. People studying cellular automata will, of course, be familiar with this. And it is in this particular case that this regularity of an ordinary grid is playing a nasty role because of the spurious conservation laws that I mentioned. That is even worse in the case of lattice chromodynamics. For every periodicity you have in lattice chromodynamics, you create a pseudo-particle with either one particular mass or one particular momentum. And of course this is nonsense, right? We do not have a spectrum of quark masses that sort of is like a regular grid between points. You can do general relativity in this way. That's of course already well known. The only thing that then you would have to do is adjust your distance recipe, because that, I must remind you, is the second degree of freedom that we have. The people around Professor Moll at Utrecht study quantum gravity effectively using this type of technique. Going back to the application where you use the Voronoi cell walls, of course they all come together in triples, and that allows you to do Feynman diagrams precisely in this way, where you transport things along this grid according to the Feynman rules, rather than according to the rules of photon scattering. One of the things that is interesting then is that you can use your point density in order to adapt to the local mass or momentum density of the quantum system that you are trying to simulate. This is a correlated point process with lots of points together here and fewer over there. And in this case, what you would see is that your point density is inversely proportional to the characteristic size, the characteristic distance between these points here. But we know from quantum mechanics that your momentum scales as 1 over lambda, right? That is to say, your momentum density scales as n to the 1 over d, and the energy density, this is just, of course, a scalar form of Schrodinger's equation, that's the momentum density squared, and the energy density squared is n over 2d, all right? So in 2d, this already is a constant, right? So those of you who want to study what happens in a two-dimensional quantum system, such as in graphene or something like that, would be ideally suited by this sort of lattice. just a few more remarks for fun, what you can do about these distance recipes. The distance recipe doesn't even have to be isotropic. One thing you can do, for instance, is have a distance recipe where the distance is given by the sum of the absolute values of the coordinates of the points. All right. This tessellation that I showed already earlier is identical to this one, except that it has a different distance recipe. All right. This, of course, is an anisotropic distance recipe, the sum of the absolute values, but still, in the mean, it is isotropic, which is kind of funny to see. All right. In some cases, you get tessellations that fragment. For instance, if you take a distance recipe as given by this expression, and you see what happens for various values of alpha, this, of course, is the Pythagoras distance recipe that we've been using. If you make it 1.5, then you get sort of curved walls with some of the absolute values. You get straight walls, either horizontal, vertical, or at 45 degrees. And if you make it smaller than 1, then the Schwarzschild inequality doesn't hold any longer, and your whole tessellation fragments into pieces, such as, for instance, in this particular case, where just one step further, this is the absolute values. If the power is 0.2, the tessellation fragments into different things. That is useful, for instance, if you use as a distance recipe the phase distance rather than the linear distance between points, like you do in quantum mechanics, then you have always a fragmented tessellation, which comes out to be quite useful. All right. Well, I already listed the main co-workers at present in my first slide, so let me conclude with the slide of the people who have already been collaborating in the theory group in Leiden. Christiane Helling is here. She has now moved to St. Andrews, as you've seen in the program. Alain van Marde is now at Caltech. I believe Frank Masquette is still with us. Harp Mellema, he's over there. Anyway, Jan Pieter, you've already seen, he's there. And his brother is now at Dampt in Cambridge. Erik van Rijkhorst has moved off to industry, as has Hille Ritzeveld, and Peter Wojtke is also in St. Andrews. I thank all these people for what they have contributed so far, and I thank you for your patience and your support.
Thanks very much for this background information on this. First question by Ed.
You said twice that this tessellation has a very nice mathematical property.
Mm-hmm.
Could you mention some?
Yes. The nicest properties that this type of tessellation has is that they are, even though it is based on the point process, they're isotropic in the mean, right? And the translation invariant in the mean. In other words, all those spurious conservation laws that you have problems with, in particular in the quantum mechanical applications, you don't really have. Another thing is that preferential directions that you might have, for instance, in the radiation field, you do not have in this case. The second thing that is nice is that the connectivity of these graphs is mathematically well understood. So, for instance, it is the distribution of the expectation value of the total number of neighboring points is well known. The distribution of the number of directions with respect to a given point is well known. Right. So, this means that all the errors that are still there, because after all it is not a continuum, are at least within mathematical grasp. There is a good error analysis in this sort of stuff. From my point of view, another thing that is nice is that you can have a functional relationship, just a pure to pick by you function, between the density of the point process and the medium that you're representing. I gave two examples, one where the density of the point process, the dth power, is the dimension of the gas density, the other is d over 2 in the case of the diffusive flow, but others might easily be constructed. So there are many things of this general sort. Unfortunately, however, the mathematical theorems that exist about the Delaunay-Voronoi tessellation almost exclusively pertain to a point process that is Poissonian. If you have a point process like the one that I showed in the example that is correlated or that is a fractal, then almost nothing is known. And then you have to resort to, shall we say, computational mathematics. It turns out, however, that in that case, the results that you get are still quite robust. But in that case, I must say, your question is, I cannot re-answer your question in that case because there are no good mathematical theorems for inhomogeneous point processes.
Jürgen?
Yeah, I have many concerns, but I will just mention two. Maybe we can talk afterwards about the others. The first one is, of course, there might be a good grid to describe the hydrodynamics and to solve the equations on that grid. But I understand that your tessellation is choosing a grid that is optimal to solve the radiative transfer equations. Is that right?
That is a possible choice that you have. One thing that one might, for instance, do is to take as the function that maps one to the other let me give one particular example, right? So rather than trying to be general. Suppose that you had an AMR simulation, which you would naturally use in 3D, right? Then you, for every AMR box, you can take your point process according to rho to the power d, for instance, scribble points over there, and then use that result to map the whole thing. So that as it were, you do adapt to your AMR density distribution in boxes, but you mitigate the effects of the directionality of the AMR grid by just using random points inside every AMR box. We have experimented with the properties of the grids that you get in that case, and they are robust, they behave well.
Yeah. I mean, we have quite some experience with multi-wavelength grids. That means grids that are not based on the density distribution, but try to find a grid that is solving the radiative transfer equation optimally. And then, of course, you have to do this for different wavelengths. And our experience is that you need a grid that is adopted maybe to very anisotropic radiation fields, as you often have in astrophysics. And that makes a tessellation, in my view, very hard for such a problem. And secondly, you have to deal with very simple things like transporting a beam through a grid. And we did it for a regular grid, for example, and because we used the first order, that means we consider only the next cell, we got second order numerical errors, which are numerical diffusion, very well known, and they smear off the beam completely. That means you have to run the beam and in the end get a beam that is still very collimated, and you don't get that. And in radiative transfer, this is very sticky. So I would like to see, if you run a beam through such a tessellation grid, if it comes out collimated in the end.
I have some figures on my computer here that I can show you. Just briefly, the way in which we've dealt with this is the following. First global remark I should make. In an optically thin situation, this is not the method of choice. All right? Because you know perfectly well that long characteristics under those circumstances are going to beat everyone. So that's all. Okay. In a combination of situations where you have optically dense and optically thin regions adjoined, it does relatively well. Yellen has programmed one particular version of the simplex method where one of the properties that the radiation has when you transport it along the grid is that it remembers its original direction. All right. If you include that in your point-to-point process, right, then you get very tight beams indeed, and I can show you some examples of this. Even so, if one were intent on having a directional laser beam, as it were, through an optically thin medium, then this is absolutely not the method that we would want to use. Do you have more concerns?
Oh, much more, yeah.
We'll get to that.
Your cosmology simulation, that was, you showed actually a sphere, but was that actually a periodic box calculation? Or
That was, no, it was not. That was one of the earlier trial simulations.
So that was
the Iliev et al. Project. This had periodic boundary conditions, because those were set by the conditions of the comparison project, where you simply took that.
Okay.
What about the optical fit case? In some sense, that's trivial. You have a diffusion approximation, but you're wasting effort here about putting 1 point for every nuclear path. What if you have an optical depth of 10 million or what?
Absolutely. That is the converse to what I was just simply saying a moment ago. In the limit where you already know that your physics tells you that the mean free path is infinitesimal, right? You wouldn't want to waste any points there. In the intermediate case, where you want to couple the photons to the fluid, but there is still some relative drift, then this rho to the power d over 2 is the method of choice. If one already knows that there is a certain part of the flow where everything is practically isotropic anyway, you would do it differently. We have not made any applications of this sort. Just from the top of my head, I would conjecture that what one would want to do there is to have, as it were, a grid where the number of points sort of refines itself. So effectively, first, you use 10,000 probe points according to this rho to the power d thing, and then suddenly you're going to find out that there are regions in the flow where already you're overdoing it, and those you will not further refine. All right. We did a few experiments, but not just very, very preliminary experiments, as it were, where it turns out that if you do this, then effectively that turns out that you are refining your grid, you're sprinkling your points where the gradients are. This is another strategy one might want to use. Because you know perfectly well that on the left-hand side of tau equals 2/3, they're just simply flying into each other. To the right-hand side of tau equals 2/3, they fly all over the place. So you want to be in the middle. That is another strategy that you might use. Even so, in my opinion, that's a matter of programming. Right? If one were to come up with a representation function, so the point density n equals some function of the gas density or the temperature, don't know what, right? Then one is still at liberty to choose that representation, right? And one might want to choose gradients, and then perhaps your difficulty is automatically certain thing.
As far as the accuracy is concerned, you are completely free still, I presume. If you want to calculate derivatives, you can put higher order paraboids.
Coming back to Ed's question, it turns out that the computing derivatives on this particular grid, okay, on the Delaunay grid, is very, very nice indeed. This is extensively used in data analysis. Rien van der Weijgaard and I, who originally started this sort of stuff in Asserbilly, in the course of the years, contacted a large number of people, most of whom do data representation with these techniques, with stuff called nearest neighbor interpolation and stuff of that general sort, where the weighting function over those points inside the Voronoi cell is in many respects optimal, as well as you can do with the amount of information that you have about the nearest neighbors. And that is in part due to the fact that your derivatives are so well determined. The nice thing about it is that because the expected number of the expectation value of the number of nearest neighbors in 2D is 6, because it limits to the hexagonal tessellation, you have more than enough information to do a second derivative on one tile. Okay, so you have a second derivative and then some redundants that you can use for maintaining accuracy. The number of nearest neighbors in 3D is 14.4 something or other, so there it works even better.
Great, thanks very much indeed. So we have now time for a discussion. We are quite free in discussing whatever comes up, of course. One aspect that strikes me as being important and useful is perhaps the realization that we are really having 3 different communities here in one. And when Bob started off by talking about line sectors, for example, this is perhaps a concept which people in other fields have maybe not really heard about. But maybe there are other issues which are resulting from a clash of different communities, and I think that's important to get over this first stage, perhaps. Are there any observations in that respect? Bob.
I'd compliment it. Yes, because one of the things that Bob didn't tell us and the other simulators didn't tell us is whether they computed the helicity density of their flows, because I know lots of people who aren't here who would like to know that. Is that something any of you have looked at?
We have looked at
The plunging plumes, for example, are they helical?
we've looked at their vorticity.
Helicity density.
Yes.
That's considered a, vital.
Yes, we have made graphs.
And have you something kind of just global to say about that?
I don't have anything global to say. I haven't done it for the case where we put in a rotation yet, but I don't.
Rotation, of course, will
I've done it in the case where there was no net rotation, and of course what you find is that there's a lot of vorticity. There's a lot of vorticity in the downdrafts. It's all wiped out in the upflows because they're diverging. Typically, in the downdrafts, you have a ring vortex at the head, which is connected back up to the surface by two or more trailing vortices. And if anybody wants to see, I can show some of the pictures of those.
Paul?
Is that why those circular cross-section features appeared as you went from the surface downward? Were they vertical structures?
I think so, but I'm not sure.
Any other thoughts? What?
Just a general comment.
Yes.
I hope that we give some time to stating the equations we're solving in the different subfields. The first talk did that. The later talks didn't do that, so understandable, since when you talk to your own community, you don't take the time.
Right. I think that is perhaps important. Should we redo this at this point? I mean, basically, of course, Bob is solving the hydrodynamic equations with a ionization that is not explicitly time-dependent. So there's no d by dt in the ionization fraction. That is something that will be different in one of the talks, or two of the talks this afternoon, I believe. So ionization is variable. Equation of state is a realistic one from a table lookup. That is another issue.
You have to be careful about ionization. I mean, where we are, it's...
Stand up, maybe. Sorry. But easier for the rest.
You have to be careful about ionization. Where we are, it's dense enough so that LT is pretty good approximation. Go up to the chromosphere, and some of the stuff that Max and I did showed that because of the slow recombination rates, that the ionization is at equilibrium.
And that's indeed the circumstances. Yes, Aristotle.
This is a question for Robert Stein. So you calculated you showed in your calculations the frequency spectrum of a solar T-month, correct? And you said that it matches up with observations. How do the amplitudes that you calculate match up with observations?
The velocity amplitudes are close, but the intensity amplitudes are somewhat different.
So by intensity, you mean the luminosity perturbation?
Yeah.
You mean the contrast in the granulation?
No.
Oh, no.
Well, there's some dispute about the contrast in the granulation. Okay? We think we're right about that. But I was talking about the amplitude in the emergent intensity in the oscillations.
So, so that means your code is not connecting the velocity perturbation or the fluid displacement to the luminosity perturbation.
It's yeah, I have to go look back at the figure, which I can look up because I don't know exactly, but I do remember that that for some of the modes you get a small, I think it's for the radial mode, you get a small intensity variation than is observed.
And can you also in your calculations, quantify the leakage rate, i.e., how much, what is the power of acoustic energy that's leaking out of the star into the chromosphere?
I have not done that. I don't know if any of the P-mode people have done that. I know that some of them are using these models to calculate kernels. And so they might have some information about that. I personally don't. I just don't know.
So as far as the original question of Paul's is concerned, about the differences, I mean, about explicitly stating the equations, are there more things that come to mind that have not been displayed explicitly? Ed is pointing to Vincent, but Arnold has a question.
Well, so this is more slightly off, but it's about this different community. So,
maybe.
Yeah. There was this thing which I don't know because I don't know the background of the problem, but Oleg mentioned that he found a different result from one of the previous talks about the bisector method, I guess it was. And so I don't know, is this very interesting that it's different, or is it just a small detail? Or, because I don't work.
Does anybody want to respond to this, or do we need Oleg to repeat this statement? Maybe you repeat it briefly.
Well, basically, bisector is the way to characterize the symmetry in the spectral lines of very different objects. It can be stars, it can be something else. And bisectors is another way to say that the lines are symmetric. And the statement that I made in the talk was just pointing out that in previous talk it was said that there is a straightforward connection between the topology of flows and the line of symmetry. And I said that when we look at the A stars, we see basically the same topology, like in solar type stars, but a different asymmetry in the lines.
But you said there were two different codes which gave different. There was another group who got a different result?
No, I was just saying that there is no one-to-one correspondence between topology of the flows and line of symmetry.
Oh, right.
Nobody else did A-star simulation before.
So, but this is due to the A stars then?
Due to the topology, due to properties.
Due to the physics?
Yes.
It's not numerics at all.
No, if you take solar simulation, like Regent simulation, and then you look at the synthetic profiles, you see that the symmetry goes in the right direction. So actually, we can fit pretty well the observed lines. So it's a combination, as Oleg said, it's not only the topology, it's a combination of the correlation between the velocity field and temperature and maybe something else, because in the case of A stars, it's still not completely understood, while in the case of the sun and the giants, well, that's pretty much understood.
Okay, first.
So, let me use this example of bisectors as a way to talk to the other communities. The bisector diagnostic in stellar atmosphere is a perfect example of a fingerprint thing. Without going into details, it encodes two things. It encodes velocity and intensity fluctuations. It's sort of a cross product of the two. You can combine that with one piece of other diagnostics, namely the line width, which encodes velocity by itself. So those two together is a very good handle on a global property. So when you're doing complicated numerical simulation, there is almost no way you can test it. But to match a fingerprint against the same thing observationally is an excellent test. That philosophy can be applied to many other situations as well. For example, if you do a transform molecular clouds, then that too is a very complex physical situation where you have enormous fragmentation, for example. But one can find fingerprints. In the case of molecular clouds, for example, the statistics of the extinction You can measure extinction of stars that are behind the cloud, and statistics of that is a fingerprint. Correlations of antenna temperature and line shift, for example, measured by velocity, 3D cubes of position and velocity is another fingerprint. And that technique is extremely general in any context. So I would sort of advocate that. Try and find sensible fingerprints. Of course, there are many fingerprints that are insensitive to making mistakes. Incorrect models can give the correct fingerprint, the correct answer for their own reason. But if one combines the idea of a fingerprint with really trying to ask, how can I get sensitivity of two different things, or several parameters to intersect, that is a very useful technique.
Mm-hmm. Thank you. Paul.
One distinction which I think we might want to emphasize as we talk about different problem areas is whether or not the radiation contributes to the momentum equation. In the cases that we will be talking about for the cosmological effects of primarily in these talks ionizing radiation, there's no effect of the radiation on the momentum equation directly. And I think that's very different to stellar atmosphere.
I think it was, yes, basically always neglected, except that Hans mentioned, of course, the Eddington limit, in which case he would begin to worry. But you did not include it.
No, it's not included. However, I should point out that they're just working with Susanne Hüfner and Uppsala on getting radiatively driven beams to work together with the stellar envelope. In this context, of course, the radiation pressure is important.
Why is the radiation pressure not important in pure electron scattering situations or in hot star?
It's very important on dust. It's very important on dust.
That's right. I just thought it came up more somehow. I thought we were.
There is a talk coming by the side of the radiation to contribute to that. Really important.
Want to stand up? You had a question anyway. First.
Yeah.
Stand up.
No, I just wanted to say, I mean, it depends on the situation you're treating. If you really have a strong affinity source like dust affinity or in the agent system where it's in the dust kind of dust in the agent system where it's in a strong affinity for molecules, you can easily vegetate the atmosphere due to momentum transfer and photons, which is very different to what involves in planets here, because the luminosity of the objects are so low. It means you simply don't transfer enough photons onto your matter, onto your gas dust mixture. So therefore, people of course do at the beginning estimate how important this source would be, and then they turn over it for photon goes it over the weather. But if you go for HV stars and you see how the winds are driven by radiation pressure on dust, then of course you do bother, and it gives you a good hope.
Thank you. Hans.
Just for completing, at least from my perspective, these issues, the DDT term in the radiative transfer equation, the time derivative, at least in my applications, are usually also neglected. Maybe it's a chance to the disk community or
we often neglect them also, but there are situations, for example, when a very strong source like a quasar turns on and is very short-lived, the finite speed of light, the ionization front will propagate close to the speed of light, and you must take that into account.
Jelle Ristenfeld did some computations of that sort with this method. Started doing some experiments with light echoes, such as well-known happening around novae and things, and also the ionization subjects, as Paul said. So it's being tried every now and then.
Mitch was half raising his hand at one point, but now he's not.
Well, I mean, I wanted to just ask about whether people had really tried to simulate convection in extremely massive stars where you're basically dominated by radiation pressure. I mean, I've encountered a situation in trying to form first C black holes at redshifts 10, where you're dealing with essentially 10,000 solar mass stars, which are completely convective, and it's all entirely radiation dominated. And when you run out of convection and go from the convective zone to the radiated zone, any slight fluctuation up in the opacity is going to lead you to exceed the limit. So
there was a thesis on that in Manchester 35 years ago. Convection in supermassive stars with radiation bubbles, photon bubbles, by Virginia Stanton Paul. Mixing the theory of photon bubbles. I found it questionable, but it was an attempt. Probably nothing happened since.
I mean, obviously the question is up to many people's minds, and they have not really attacked this problem as yet. And maybe this conference will help bringing some people over the limb to actually do it.
May I ask a question?
Please, yes.
I'd like to ask the question and not expect an answer maybe till Friday, but most people throw out the time derivative from the transfer equation. I take that back. Many people do that anyway. And one of the things being thrown away in that neglect is the retardation time between the production of the photon and its arrival at the place of interest. About 20 years ago, a thesis was written by Christian Fröschle under the direction of Philippe Belache, in which they studied radiative cooling processes in which you have pure scattering, or scattering important, and including the retardation effects. And they found that this produced a non-negligible influence on the cooling times. So is anyone worried about that or not? And if so, please tell me what you think is going on. Should we be worried about such effects? Because I've never seen anyone refer to that thesis since that time. Of course, the last guy or something, but still.
Sorry, cooling of what? I mean, what object? That's important.
Pardon?
The object you have, or the
No,
timescale.
just you have a medium and temperature fluctuations, and there's scattering, electron scattering and so on, and you compute cooling times on the inhomogeneities. No particular object was mentioned.
No, but if the object is, evolving on a certain timescale, if a cloud is forming on Earth.
Oh no, of course,
and it
this
has
is
some
no
timescale,
underlying evolution, or at least you could imagine a two-time process. No, just a medium. You impose fluctuations and ask how long they last. Radiation is active. No one is moving, nothing is happening, but you allow for the fact that there's a retardation function. And that affects the cooling. And the reason that you have to allow for it in her vision was that a scattering process, the photon is always there, it does not forget its origin. And if you hang around long enough, you get an effect on the cooling times. And that was worked out explicitly. It's within the limits of, I think, linear, some kind of linear thing. So there was no object except the world, so to say. Anyway, if you have thoughts about it, please let me know during the week, because I've never seen anyone thinking about it.
Any response right now to this?
I guess I'm trying to understand what the effect is. That's what I'm not.
Well, it just, you can write a heat equation, except instead of a Gaussian of T, you get some integral operator. And then you can compute the decay times of fluctuations. Now, if in your integral operator, which is a transform of the local source function, there's a retardation time between what happens over there and what happens where you're interested. If you neglect that, which amounts to neglecting di dt in the transfer equation, you get one answer. You include it, and you have scattering, so photons last a long time, then the answers change, and it's not a negligible change in many cases.
I would think it would only be relevant in situations where things were changing on a light crossing path, and otherwise.
Yes, of course. Well, but if it's a scattering process, these things last a long time. They don't go away. So they do this, and it's the same photon remembering how things were there. So if things have changed since then it's a different message.
Crossing time, it might be.
Oh, sure. If they try. Of course, that's the point. Yeah. Thank you for the clarification.
In large-scale cosmological radio transfer simulations, the multiple scattering usually isn't an issue because we're looking at ionization fronts on megaparsec scale.
And you're also changing the photons through the expansion. So
then it's important. That's right. You have a look-back time.
Yeah, that's right.
And the light cone evolution. And that is important in certain problems.
All right. I think one issue that Bob raised, of course, but we won't have time for that now, was, of course, the issue why many people use flux-limited diffusion approximation as opposed to real radiative transfer. And that's maybe another issue that we should talk about during one of the upcoming discussions.
I wasn't thinking about compared to real radiative transfer. I was thinking about taking the next moment, so you have one less arbitrary relationship.
Okay, so I think now it's time for lunch. Lunch is, we can just go there and pay, or you have your ticket, in which case the payment goes faster.
Can we leave it here?
Yes, it will be locked, and will be open shortly before 2 o'clock. Yeah. I hope that's reasonably safe, yes. Let me check that.
What was this mail sent out about?
I'm sorry. I think they should be locked. Do we have a lock for this? Yeah, that's okay.
Thank you again.
Now that's amazing, right?
So what's your
could you maybe check about the lock time, that it will really be locked during a certain period automatically? Otherwise it will actually, it's maybe actually locked all the time already, right? Maybe we should import it.
Be careful with your battery.
Now they repaired it today. They repaired it today, so it's just that they will tomorrow again because they said there was something else
You get some hints. It was very
Number of photons.
Can you go